Welcome back. So we'll continue the discussion on the conservation law. So before we go further, so we'll discuss some examples and let's start with what is meant by a conservation law. So again, this is motivated by fluid flow problem. So imagine a fluid flow, and so there's some imaginary domain within the fluid omega. So at any time, the mass of the fluid within omega is a constant, and that's termed as uh, conservation of mass. And motivated by that, so there is mass comes from the density. So we have some general definition of conservation law. So U is density of that substance and F is its flux. So here that fluid, so suppose the fluid is in this direction, arrow of the direction, then fluid enters this domain and some fluid leaves this domain, and at any time interval, so we expect the uh, this conservation law to hold. Okay, so this is the this is density. So this is gives you, if it's density of the fluid, it gives you the mass of the fluid in omega that is present between two times T1 and T2, T8, and that must be equal to the whatever the amount of fluid that has entered the region and left. At T1 it has entered and at T2 it has left, and so there is actually this should be equal to minus, so I am taking that as plus. So this F is the flux and nu is the outward unit normal as usual. Okay, so this is a general statement of a conservation law. Okay, and when most of the time we are dealing with one dimensional thing, so this omega is replaced by an interval. Okay, so we'll see an example of traffic flow that is one dimensional. So this is the conservation law in integrated form. So this, for example, from fluid dynamics, gas dynamics. So this conservation of mass, momentum, and energy, they all appear in integrated form. Okay, under appropriate assumptions on the continuity of the functions involved, so we get the differentiation in the conservation law in differentiated form. So that is an differential equation. Okay, so first you divide by T2 minus T1 and let T2 go to 0, and there that gives you this ut here. So omega, integral omega ut, and this side you have only this integral, surface integral. Okay, this when you divide by T2 minus T1 and let T1 to T2, so that will give you only surface integral, and then you apply the divergence theorem, so that becomes divergence of F, and then if you combine these two, you get integral over omega of this quantity ut plus divergence of F equal to 0. So for that is true for all omega. So once you shrink omega, so assuming that this quantity is continuous, so we derive the conservation law in the differentiated form. Okay, so in deriving this mass, momentum, and energy conservation equations, so we need to take different U's and different F's. Okay, so here I have just written some terminology, but for more details you should consult a good book on fluid dynamics. Okay, so now coming back to a fluid flow problem, so these are the usual notations. So this is rho is mass density, and capital M is rho times V the velocity, so that's a vector again. So there are three components in Cartesian coordinates, so that is called momentum density, and then there is energy density and internal energy. So all these quantities, so if you want to know more about their physical significance, you should read some good book on fluid dynamics. And then using this conservation principle, we derive this system of equations. Okay, and then of course this there are 1 2 3 4 5 6 unknowns, but there are only 1 3 4 only 5 equations, and to make it a self-contained systems, so many assumptions are made in the context of fluid dynamics. uh, okay, so one usually gets this uh, system of Euler equations. Okay, so you just uh, go through some good book on fluid dynamics, and in fact fluid dynamics gives you lots of uh, models for this conservation laws. That is main source, in fact that's the main source. And second example is traffic flow problem. Okay, so this is again one dimensional, so here just, so this is a long highway, okay, infinite highway. Okay, so that's along the x-axis. So this is what we are proposing here. This model is a single lane problem, so one can also incorporate multi-lane. So big highways are now, there are multi-lane highways, so that's more complicated. So here this is just uh, a single lane, and that too in a unique direction. Okay, so if you include again both way traffic, this will be more complicated. Okay, okay, so here is the simple model. uh, so let uxt denote the number of vehicles passing through the position at x and at time. Okay, so though this is a whole number, we treat this as a continuous variable. Okay, that's usually what is done in most of the modeling problems, even fluid flow problems. Okay, so there are actually finitely many particles, but then there is continuum hypothesis, etc., which makes it possible to consider as a continuum. Okay, so those are some of the philosophical questions. Okay, so similarly here we are doing that. And let Vxt denote the average local velocity of the vehicles. Okay, that's where speed, local speed. Okay, and let's assume that at any uh, interval x1 x2 on this highway, so at any time t, the number of vehicles within this interval x1 x2 is a constant. So that's the assumption of conservation. Okay, and that leads to, okay, just again look at this. So that u, number of vehicles, is our density now. Okay, and the flux will be u times v. Okay, so u is the average velocity. Okay, and so that relation leads to, in the present context, so this at any two times T1 and T2, assuming that this number of vehicles in any interval is preserved, we get this conservation relation. Okay, and again you divide by T2 minus T1 and let that go to 0, that difference. So we get left hand side, we get integral of u sub t, so that's the derivative, and right hand side you get vu x1t, vu x2t. Okay. So in this relation we easily see that vu denotes the flux. Okay, and again you divide by x1 minus x2 and let that go to 0, so then we get, so this is the actually this one is the conservation law in integrated form. And provided the quantities in question are continuous, so ut should be continuous and this vu should be continuous, and this is the conservation law in differentiated. So that is a differential equation. So again, first order equation we get first order partial differential equation. And now we make some reasonable assumptions on the local velocity. Okay. So obviously we can assume that this local velocity is a function of u. Okay. So as experience shows, the drivers of the vehicles increase or decrease their speeds, okay, then that is v, according as the number of vehicles, and that is density u, decrease or increase. Okay, if there are less number of vehicles on the road, the speed will be increased, and if there are more number of vehicles, obviously the speed will be reduced. Okay, and when the density is maximum, okay, so almost all vehicles will come to a standstill, and that represents almost zero velocity. And in any even if the density is very low, usually there are speed limits, so this the velocity cannot, the speed cannot exceed certain limit. Okay, so when density is very low, so v is almost that allowed limit, that is v max. Okay, and so that represents v max there. So when u is uh, so if the density is 0, obviously there is no vehicle, so speed is obviously 0, and again when u is that maximum possible density, and then again v is 0, and so there is a maximum uh, speed. Okay, and in this case, looking at the graph of this fu, we see that f is a concave function, and so this uh, conservation law is a concave conservation law, but most of the theory that we are going to study applies only to convex. That's the main assumption, convex conservation law, that is the f, the flux is convex, but that's easily turned into a convex law by changing the sign. So if f is concave, minus f is convex. Okay, so that's not a problem at all. So this traffic flow problem also very well fit into the general theory of convex conservation laws. Okay, and I just mentioned here some other examples. The model equations from many fields come into this form of conservation laws, and these fields include electromagnetism, magnetohydrodynamics, hyperelastic materials, chemical physics and engineering. Okay, there are processes called electrophoresis and chromatography. So these are again very good models, and these have benefited lots of industries. And there is also combustion theory. Okay, so these all fall into this subject of conservation laws. Okay, so these are some uh, important class of examples. Of course, major part of the problems, they come from the fluid flow problems. Okay, so with those examples, now we proceed to uh, discuss the solutions of the conservation laws. So let me again start with this. So usually we assume this f is at least C2 function, and more assumptions will follow. Okay, and this is an example of Cauchy linear first order equation. So this can be solved by method of characteristics as long as the characteristics do not meet each other. Okay, so that we have already seen in first part. Okay, so let's now see if how the discontinue develop. How should this solution behave across a discontinuity? Okay, so let U be a weak solution of this uh, conservation law. Okay, and you take any open set in R cross R plus. Okay, R plus here is the positive real axis, and let this gamma be a curve. Okay, sitting in V. Okay, so we assume that this weak solution, as we discussed in the previous class, so the definition of weak solution gives us an integral relation. Okay, in terms of the test functions. So suppose we assume that, so this is our V, and this curve uh, divides this domain into two parts, VL and VR, L for left and R for right, and assume that this weak solution is C1 in both these parts, so left and right. So, and this is the gamma is the curve of discontinuity. Okay. Gamma is the curve of discontinuity for the solution. Okay. So we also assume that this limit of u when it approaches from the region VL approaches this curve gamma, it has a finite limit, and similarly when it approaches from the region VR, that's also finite, and call them those limits UL and UR. Of course, they depend on this which point we are on this curve. Okay, So UL are functions of t, okay, across this gamma, and UL is not equal to UR. Okay, so that's discontinuity. Okay, and since we are assuming U is C1 and in both VL and VR, as we saw in the previous class, this U satisfies the equation both in VL and VR. Though it's a weak solution, but since it is C1 here, so at those points it satisfies the differential equation pointwise, both in VL and VR. Okay, and now you start with the definition of the weak solution. Okay, so we are assuming U is weak solution. So this holds true for all test functions phi. So there is another term coming from the initial data, but if we assume that support phi is in V and 0 is not included there, so that phi x 0 is 0, so that other term is not there. Okay, and since this V is union of VL and VR, so that's the advantage of the integration. So we can write that as sum of two integrals, one over V sub L and another one from V sub R. Okay, so consider for example this V sub L integral over V sub L, and here, so since we are assuming U is C1 in V sub L, so we can integrate by parts. So when we integrate by parts, we get that first term, and then there is a boundary term. Okay, so just remember there is a boundary here. Okay, and what matters is this values on this gamma and values on the other part of the gamma VL are taken care by the support of phi. So they will not be there. So only that integral over gamma appears. Okay, so you apply Green's formula. Okay, so you apply Green's formula, you get that. And in VL, we already seen that this is 0. Okay, so that vanishes. So this integral over VL reduces to this line integral, where this nu t and nu x, these components of the outward unit normal to gamma. Okay, so let me just change that. So this is gamma. Okay, so since it's outward unit normal, so for the part V sub L, this normal points towards VR, and for VR it points towards VL. Okay, so there is a sign change, so that we should keep in mind. And this is the line measure, if you want to call that. It's just, this is a curve, so this is line integral d gamma. Just that is notation. Okay, so this is a line integral. Just remember that. This is from the Green's formula or divergence theorem. Okay. And that gives us, so this term vanishes. So this integral over the region VL just given by this line integral. And similarly for the region V sub R, it's again a line integral, and as I said, this sign changes, so we have minus here. Okay, because the direction of the unit normal changes, so we get this minus sign. Okay, and now you add these two relations. Okay, so this integral over VL plus integral over VR is equal to integral over this line integral over gamma and this line integral over gamma. But the left hand side, if we add integral over VL and VR, and that is 0. Okay, that's how we started with this. Sum of these two integrals is 0. So, and that we get, so this UL minus UR nu T, F of UL minus F of UR nu X, whole multiplied by that test function phi is 0. Okay, so here I have denoted by this square bracket. So these are jumps across gamma. Jump across gamma. And that jump induces a jump in the flux here. Okay, so this is jump of U and this is jump of F of U. Okay, just by adding these two relations, we get that. And again, since phi is arbitrary test function, we should have this relation. So this integrand vanishes. Okay. So this holds along the gamma. And this is referred to as Rankine-Hugoniot condition or simply jump condition. So any weak solution of the given conservation law, okay, that's first order PDE. So any weak solution of this conservation law having a discontinuity along a curve, okay, and smooth on either side of the that discontinuity curve must satisfy. So this is a necessary condition. Okay, must satisfy this Rankine-Hugoniot condition. Okay. So now we can rewrite this in more neater form. If you assume that this smooth curve is given in terms of a function, namely x equal to st, okay, so we can express the components of the unit normal in terms of that s. Okay, so this so gamma is described by this curve x equal to st, and s dot denotes derivative with respect to, and so that denotes the speed of the this discontinuity curve. Okay, in terms of s, we have nu sub x, the component of the unit normal, unit is 1 plus s dot square to the minus half, and the t component is minus s dot 1 plus s dot square minus half. Okay, so if you plug in that in this, so there is a nu t and nu x, and do some simplification, what you get is f of u, the jump across gamma is given in terms of jump of u multiplied by that sigma. Okay, so sigma, okay, I forgot to write this. So sigma, so this is minus. Okay, they are functions of t. Okay, just remember that. Okay, so this speed of the discontinuity curve is expressed in terms of the jumps of the solution across that discontinuity. So this is an important relation that every weak solution must satisfy. Okay. Our next discussion is regarding the uniqueness question. Okay, so this example is with regard to uniqueness of the weak solution. Whether one can have more than one weak solution. Okay, so and this example is towards that. So consider this Burger's equation. Again, ut plus ux equal to 0. So in terms of that f, so here in this case f of u is half u square, and let the initial data be given by this u0. So u0 has discontinuity at x equal to 0, so it's 0 for x less than 0 and 1 for x bigger than 0. Okay. So the characteristics in this case are very simple. Okay, just you can recall from what we have done in the first part. So for x, so these are in the xt plane. Okay. So for x less than 0, the characteristics have 0 speed here. That comes from this 0 initial data there. So they are all just straight lines. So x equal to constant. So I have put some arrows here. That is just to show that, so in this case of course they are constant, so there's increasing time. Okay, and for x bigger than 0, they all have the characteristics, they have all uh, speed 1, so they are just given by, so these are the curves. So any general curve here is just x plus some x0. Okay, so if this is x0, okay, so this is so they're all have slope 1. Okay, these are the characteristics, and that leaves this portion. This portion, what is that portion? So this portion, no characteristics. So the method of characteristics does not give any value of the solution in this region. And what is that region? So this is just 0 x by t less than 1. That's the reason. Okay. So the method of characteristic just gives you this u of xt equal to 0 if x is less than 0. So we are interested only in t positive. So I'm just testing that. And 1 again if x is bigger than t greater than 0. So this leaves that region 0 less than x less than t. Okay. So the method of characteristics will not give you any solution there. Okay. Now we try to construct solution, weak solution for all x and t. Okay. Now consider these three functions. So I am defining three functions here. So u1 of xt. Okay. So I am defining for all t is positive. Okay. So that's want to only define for x t positive, right? So that's at t equal to 0, we are given that initial data. So u1 of xt is 0 if x is less than t by 2 and 1 if x is bigger than t by 2. Okay. Of course, any constant is a solution of the given equation. Any constant is solution. So only it need to satisfy the initial condition. So in all these cases, we are just gluing two appropriate constants to the left of a line and to the right of a line. Okay, so here you can see So when t is 0, can take the limit. So x less than 0 we get 0, and x bigger than 0 we get 1. So that initial condition is certainly satisfied, and since they are just constants, so they also satisfy the equation. Okay, and so here the discontinuity is given by x equal to t by 2. So we'll see that. We'll see. Okay, and again here, so u2 also consists of three constant states. Okay, so 0, half, and 1 in different regions. Okay, and now this is if x by t is 1 by less than 1 by 4, and half 1 by 4 and 3 by 4, and 1 if x by t is bigger than 3, 4, and one more function. Just let me define that, and then we'll analyze all the three solutions. So u3 xt is 0 if x by t is less than 0, and x by t if 0 is less than x by t less than 1, and 1 if x by t bigger than 1. Okay, so let's consider this first function u1 of xt. Okay, so x equal to t by 2, that is the line of discontinuity. So in this case the curve is a straight line, x equal to t by 2, and so we have on the left we have the value 0, and on the right we have the value 1. So if you plug in this into this jump condition, you easily see that the jump condition is satisfied. So let me just say that jump condition is satisfied. Why? So in this case we have constant speed, so sigma is just half, as x is t by 2, so yes, t is t by 2, so its derivative is just half. And as I said, this ul is 0 and ur is 1, and our f of u is half u square. So you get f of ul is 0, f of ur is half. Okay, so if you plug in all these values, so you get half equal to half. Okay, so jump condition is easily seen to be satisfied here. Okay, and you can even put in these values, so these are just constant states, so it's easy to verify that it's in fact a weak solution. That's not difficult at all. Okay, the expressions are just constants. And what about u2? So u2, we see there are two lines of discontinuity, namely x equal to t by 4 and x equal to 3 by 4t. Okay, and again the value is 0 here, half there, and 1. Okay, so we are just joining these constant functions by these lines of discontinuity. And as we did here, so you can easily check that the jump conditions across both the discontinuities. So here we have one x equal to t by 4 and here x equal to 3 by 4t. So again jump conditions are satisfied. Now there are two, so you can see. What about u3? u3 there is no need to verify, the jump condition, though apparently you see that x equal to 0 and x equal to t, but across those two this u3 is continuous. So all three, so namely u1, u2, in fact you can even produce many more, are weak solutions of this let me write that. This ux0, u0x. Okay, so certainly the uniqueness is lost. Uniqueness is lost. But uniqueness is an important requirement in the study of uh, any physical situation which will not like to have multiple solutions. Okay, so which one to choose and which one to reject? Okay, and that's where the physics has to enter into picture, the physical situation. And it was Lax who first proposed this, what we call Lax entropic condition, or simply entropic condition. Okay, so let me write uh, the condition, and then we'll see which one uh, we should keep as a solution and which we should reject. Okay, so here, so the characteristics, so this is initially looks little complicated. The characteristics from both the sides of a discontinuous curve, and this is also called, so this also we said already, also called shock. Shock should impinge upon upon the, I will say comment something like that. Okay. So here is x and this is t, increasing t. So this is, say, shock. Okay, so this entropic condition means, suppose these are the characteristics from this side. Okay, so this is the entropic condition. Okay, so if you look back again these examples, okay, so you see, that's why I've drawn that arrow. So entropy condition is not satisfied. Okay, so in this case and also in this case. Okay, so for this region, okay, this, because of this failure of the entropy condition, these two solutions are rejected. Okay, so here the question of verifying the entropy condition does not arise because U3 is continuous. Okay, and this has a name, so this is called a rarefaction. Okay, so it's a constant state on the left of this. So this is like a fan. Okay, in fact it's called, also called fan wave. So this fan wave joins these two states 0 and 1 continuously. Okay, so at the left it joins 0 and at the right it joins 1. Okay, and over the years this entropic condition has gone into many different forms. So obviously this is somewhat uh, tedious to verify in a given situation, but for so that's what Lax observed. So for the strictly convex F, strictly convex F, so in that case we call the conservation law as strictly convex conservation law. This entropic condition is equivalent to say UL is bigger than U1. So remember, UL is the limit of the solution as it approaches the discontinuity from the left, and U sub r is the value of the solution as it approaches from the right. Okay, and even in that, so in this case this half U square is strictly convex, there is no problem with that. So here we have on the left it is 0 and on the right 1, so that's violated. And again here it's on the left it is 0 and here it is half, again that is violated. And here on the left it is half and on the right it is 1, again that is violated. So even for the other region, so this so this is somewhat simpler. Okay, but this applies only to this strictly convex F. Of course, we are dealing with that. And nowadays, this entropic condition, so this is the result of many years of research. So this now stated in the form of an inequality. One-sided, a one-sided. Very elegant form. So we'll discuss this after we obtain Lax-Kolinic formula. So it combines the earlier versions into, so this is just elegant form. And it directly involves the solution. So it's in terms of the solution, and as you see, it also gives rise to, so also gives some regularity. We'll see all these things. Okay. So in order to avoid this non-uniqueness, we have to impose an additional condition. Now that's known as entropic condition, and will now, so this is an easier version of saying that. So but we'll soon see this can be stated as a one-sided inequality. Okay, so we from here we'll proceed next time. Thank you.